Hi, my name's Alan. I'm going to present some work I did at Heriot-Watt, funded on the ORCA project, and it's to do with identifying static relationships as part of domain model acquisition. And the problem in model acquisition is we've got a problem domain, take some observations from it. In this example, it's action headers, and these observations go through some process and we end up with a model which we can then use to plan. So the LOCM and LOCM2 approaches create a model of the problem dynamics. So for example, noticing that packages are loaded and then unloaded, and they can't have other combinations. And it can do that just from action headers. And these are represented by these little finite state machines, and they can uncover other kind of structures between objects as well. Okay, but it's just the dynamics, so they're missing this kind of static constraints. So in this case, the target model MT actually only allows moving from L1 to L2 and L2 to L3. These red lines at the top. Okay, but the partial model found by LOCM allows these arcs in blue, which also include moving from L1 to L3. So we're missing some kind of constraint. Okay. So we can consider some of the extensions that have been done to LOCM, in this case LOP and NLOCM. And we can approximate these with a process of having a hypothesis space, some kind of ordering. Each of the candidates can go through a Boolean test. If it's satisfied, then that's a possible solution. If it's not, then you can go into the next candidate in your ordering. Okay. In the case of LOP, the candidates were tuples of action parameters, and the Boolean test starts from optimal plans, and then each of your candidates is tested on the same problems. You use them to solve the same problems, and if they're able to solve the problem in fewer actions, then you know you're missing a constraint, and so the test fails. Okay. So LOP requires optimality, which is difficult. If you don't have a model, you just want you need to be able to say that some plans are either cost optimal or unit cost optimal, which in neither cases is necessarily that easy. Okay, so in this case, all we're going to do is focus on this Boolean test, and we're going to change the requirement of needing optimal plans. In this work, we're going to use a different assumption. We're going to assume that we've got the reachable actions. So this is all the actions that are reachable in the target model. Okay. So and what we're going to do is try and find some examples using this idea of frontier. So the frontier, if you imagine you've got an action sequence that you're building, while you're using reachable actions in the target model, those states are all okay in the target model, because we're assuming that the dynamics have been captured correctly by LOCM. Okay. And so these reachable actions are your positive examples. They're actions that are correctly modelled. As soon as you step from one of these states using an unreachable action, then you know you're missing a constraint. And so that's a negative example, right? And they're set on the frontier. But so your action sequence goes from being a valid sequence in the target model to not being valid. Okay, so these are the negative examples. Okay, and the idea here is that we're just going to use these examples as part of the Boolean test. Okay, so LOP was comparing optimal plans. We are going to use these examples, and this algorithm is given a tuple partition P and a set of positive examples and negative examples. We're going to determine whether that tuple is sufficient. Okay, to separate the examples. So in this case, we've got the tuple 2, right? So if we look in the examples, drive T1, L1, L2, so the second parameter is L1, but L1 is also the second parameter in a negative example, the first one, right? So that means that that is not sufficient to split these examples. On the right hand side we've got the tuple 2, 3, and in this case, so we can see that L1, L2 doesn't exist in the negative examples, and one of the negative examples, L1, L3, doesn't exist in the positive example, right? And this tuple is actually sufficient to split the negative and positive examples. Okay, so that's what we're looking for. So we're going to allocate a value to each of the tuple evaluations of P. So for example, L1, L2, right? True if there is an example in the data. So if it needs to be true because the data shows there is a true example, then we say it's true, and it's false otherwise, right? And then we check that that is consistent for all of the examples. Okay. So the idea then is to take that Boolean function and use it within the algorithms for LOP. So in the first algorithm, we're looking for the minimal parameter tuple. So these are the ones that must be part of the static. So we start with all the parameters, so 1, 2, 3 in the drive action, for example, and then we remove parameters incrementally and test again, right? So the tuple 1, 2 is not sufficient, 1, 3 is not sufficient. We saw in the previous slide, 2, 3 is, and then we try removing further parameters. In this case, the result is the new static with the 2 location parameters, just like in the domain. The next step is to take that tuple and try and break it into smaller tuples. So the idea is to factor the predicate, which could have, for example, 4 parameters, and try and see if there's any structure in that we can identify. Okay, so in this case we start with 4. This is a free cell example because the drive action doesn't split. So this is an example from the free cell of the move B action, which does split. And in this case we start with 1, 2, 3, 4. These are identified as parameters that do have static relationship. And then we try all the different combinations of splitting that tuple. So taking 1 and 2, 3, 4, and then 1, 2, and 3, and 4, and all the different combinations, and seeing which ones are still okay. And so we get to 1 and 2 and 3 and 4 are the only ones that work there, and then we try and split 1 and 2 and 3 and 4. And in this case, 1, 2, and 3 and 4 is as far as you can go. So we get 2 statics instead, and in this case they correspond to predicates in the domain of canstack and successor. Okay. So the results, we looked at static, which is our approach, and compared it to LOP. So static has 2 versions. In both cases we used one problem just because we didn't see anything interesting with more than one problem, but we had different numbers of expanded states. This is target model states, so we expanded all the reachable actions in the partial model for this number of target states, and this is 10 and 100. And in the 100 states case, it did well, 0 errors. Here means that it correctly identified all the parameters that must be in a static, and it also partitioned them down to separable components. In the 10 state case, it wasn't sufficient. So basically, it didn't. The states that were expanded didn't give it enough information. So it's possible that a different way of expanding states would have, random or whatever, would have allowed it to actually see all the actions, which it didn't in this case. So, okay. So, in conclusion, we presented an alternative approach to identifying static relationships based on examples, and it's not using optimal plans. And we showed that it can kind of identify static relationships. And because its Boolean function is more focused and it can operate action by action, it's also able to improve on the performance of LOP. In the future work, we'll look at different ways of actually getting examples, and also how that type of data can be used in other types of domain model acquisition. Okay, thanks.